Welcome to Pomodoro Joe for Wednesday, May 24th, 2023. Today we're looking at LeetCode problem 2542, maximum subsequence score. This is a medium problem. You're given two zero-indexed integer arrays, nums1 and nums2, of equal length n, and a positive integer k. You must choose a subsequence of the indices from nums1 of length k. For chosen indices, I0, I1, I so forth to k minus 1, your score is defined as the sum of the selected elements from nums1 multiplied with the minimum of the selected elements from nums2. It can be defined simply as nums1, index I0, I'm not going to read that whole thing, return the maximum possible score. A subsequence of indices of an array is a set that can be derived from the set 0, 1, blah, 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 deleting some or no elements. All right, so the basics of this one are we have two arrays, nums1 and nums2, and we need to select a subsequence of numbers from nums1 of length k. And we take the minimum value from the same indices in nums2 and multiply the sum of the subsequence from nums1 by the minimum value of that indexed number from nums2. So the example is kind of long. So we have 1, 2 3s, and a 2. Then we have 2, 1, 3, 4. And the k is 3. So we have to choose 3 elements from here and multiply it by the minimum matching element in nums2. So they give us some examples. You can choose 0, 1, and 2. So that's 1, 3 plus 3. And then you add those together and you multiply that by the minimum of, let's see, it's going to be 2, 1, or 3. So it's going to be minimum 1. And you get 7. So on and so forth down the line. All right, we have some constraints. But with this, we will jump in and get started. So I have 25 minutes on our Pomodoro timer, and we're going to do this in a very simple recursive way for a standard subsequence type problem. So we'll have some result, we'll set it equal to 0, and we will return the result at the end. Now in here, we're going to use a recursive function. So we'll actually create a recursive function inside to actually do our recurse. Now this one's going to be tricky because the recursive call will not just take nums1 and nums2 and k. We're going to have to pass our data down our recursive calls. So we'll have to keep track of our total sum and our minimum value in addition to the index that we're at and the remaining k. So this is actually pretty complicated. All right, so before I start coding this up, I'll just take a step back and describe where we're going with this. So in a typical subsequence problem, when you write a recursive solution, you'll be passing down the indices that you're currently at. So you'll traverse your array from left to right. So we'll be keeping track of the index that we're at, along with any other data that we'll need. So we'll definitely need our index. We'll also need to know how many of the subsequence elements have we chosen so far. So we need a remaining k. So this way we can traverse from left to right, keeping track of how many elements we've added to our subsequence. Now for this problem, we'll also need to keep track of which elements are in the subsequence. We don't actually need to know the elements themselves, but we do need to know the total value of all those elements, so the sum of those elements. We'll also have to keep track of the min multiplier, or the num2. So we'll have the min multiplier. And now we do our recursive solution. With any recursive solution, you do your base case first. We have two base cases here, but we'll start with the first base case, which is if we're out of elements, our remaining k is 0. So if the remaining k is 0, we're done, and we need to return. Well, we'll see what we return. All right, if our remaining k is 0, what is our return value? Well, we'll be returning our total. So that's the sum of all of our subsequence elements times the minimum m. That's the minimum multiplier. So that's our first base case. Our next base case is if our index is out of range. So we're done and we haven't actually built up any subsequence of k elements yet, then we'll return 0. So if index is greater than the length of our nums1. I'm actually going to put that out here. So we'll have max index. That'll save us one length call for every recursive call here. So if the index is greater than our max index, That means that we've exceeded our bounds. We haven't yet reached 0k, so this is sort of an invalid case, and we'll just return 0. Now we get to our two options. So this is our standard template for a subsequence type problem. For any element in our sequence, we have two options. We include that element as part of our subsequence, or we skip that element and move on. So let's do the easy one first. So the easy option is we just skip this element and we move on. So option 1 will be a max recurse call. Let's see. So option 1, we do a maximum recurse on index +1. We move on to the next element. Our total doesn't change, our min m doesn't change, and our remaining k doesn't change. So that's the easy one. We're skipping this element and moving on. Now option 2, that's where we decide to use this element as part of our subsequence. So this one's going to get a little bit more difficult. I'm going to set this to none to begin with. Or maybe I'll set it to 0 to begin with here. So our option 2 will actually be this max score recurse call, but we'll be passing in index +1, we'll be passing in our new total, and we'll be passing in a new min multiplier. And we'll be passing in remaining k -1 because we've selected one new element. Okay, so this will be our new recursive call. Now we haven't built all these pieces yet, but we'll get back to that in a second. At the very end here, we'll return the maximum of our two options, option 1 or option 2. Okay, so what pieces do we need? We need this new total and this new min m. Okay, well the new total, that's just going to be our current total plus the element at this index. That's going to be nums1 at this index. So we're adding this element to our subsequence, which means that we add it to our total. Now our new min m is the other piece we need. Well, that's going to be the minimum of the current minimum m. So that's the minimum multiplier, or whatever multiplier is associated with this particular element. So that's nums2 at this index. Okay, and that should do it. Now we don't actually do anything with this external result, so I'll remove that. And then down here, we need to make our initial call. So we have to actually call our max score recurse for the first time. We'll pass in 0 as the first index, 0 as our total. Now our min multiplier, we don't know what that is, but we need to make this large, so we make it infinite to begin with. And then our remaining k will just be k. All right, let's give this a shot and see how we do. And that works. So this follows the very basic template for any subsequence problem in using a recursive solution. Let's submit this and see if we can pass all of the tests. And the time limit is exceeded. We passed 12 of the 28 tests, but we don't pass all of them. All right, I'm going to grab this test case as one of our test cases, and we'll see if we can speed this up. One quick simple thing we can do here, we can use the functools cache. So from functools, import cache. Now cache lets us cache out our values. For any time we call this recursive function with the same inputs, the first time we call it, cache will actually calculate the output, store it in a cache. Then the next time we call it with the same input, it will just return the cached result. Now this might help, but we have a lot of variables here. So the more variables you have, the less likely you'll have the same set of variables each time. So this probably won't give us much of a gain. And we get a memory limit exceeded. So that means we have too many calls here and we're caching too much data. Okay, so we need to find a better solution. Now recursive solutions are generally slow. So let's see if we can find an iterative solution. And for this one, we'll just start over. All right, so let's take a step back and look at this problem a little bit more closely. The first thing that we'll look at here is this subsequence part of the problem. So at the very end, we're just adding up all of our elements in the subsequence and using the minimum multiplier that's associated with those elements to find our answer. Now the sum of the elements doesn't really depend on the sequence itself. Like you can add these elements in any order and still get the same sum. So you don't really need to keep track of the order of elements. So many subsequence problems, the order will matter. You have to keep track of the actual ordering of the elements. For this problem, since we're just summing them, it doesn't really matter what order these elements are in. So in fact, this subsequence problem is more like a subset problem. So that's going to be helpful. We don't need to worry about keeping order, so we can actually reorder all of our elements. So that's a huge clue to solving this problem. Now that we know that we can reorder our elements, let's just sort them. So what we're really looking for is the maximum sum times the maximum multiplier. Okay, that's our goal here. So let's associate all of our elements with their multipliers. So what we want to do is actually have a list of elements. So let's do that. So we're just going to go through all of our nums1 and nums2, put them together as tuples, and store those as elements in our elements list here. So I'm going to put nums1 at index I and nums2 at index I. Let me actually make it easier here. We'll call this E for element, and that's just going to be a tuple with nums1 index I and nums2 index I. And we're just going to add this element to our list of elements. So now we have a list of all of our elements, where each element in the list is the number and its associated multiplier. All right, so let's sort these. Now we can either sort by the multiplier, or we can sort by the element value. So the key to this one is sorting by the multiplier. So we'll do an elements.sort, and our key will be our multiplier. So in this case, our elements will be sorting by key, and that's a lambda function, which we're going to take the first index in our element. All right, so we're sorting by the multiplier because we know that we need the minimum multiplier when we go through our sum and multiplication at the end. And what I'd really like to do is have the highest multipliers at the beginning. So I'll say reverse is equal to true. All right, now we've sorted all of our elements by the multipliers, with the highest multipliers at the beginning of our elements list and the lower multipliers at the end of the element list. So this is where it gets even trickier. So now that we have all these elements sorted, we need to go through, find the first k elements. Those are going to be the largest multiplied elements in our list. Once we find our base value, we'll sum all these elements, multiply it by their minimum multiplier. Then we can go through and replace one element at a time to see if we can find a better score. So let me take a step back and describe where we're going with this. By sorting all of our elements by the multiplier value, it puts all of the largest multiplier values at the beginning of our list and puts the lower multiplier values towards the end of the list. We can add up all of the elements in our first k elements, get their values, get the sum, multiply it by the smallest multiplier, which will always be at, I guess, the highest index in our list. So we can multiply those by our multiplier to get a base value. That's our starting point. Now we can start checking to see if we replace one of our values, one of our elements, with a different element, do we get a higher score? Now, which elements would we replace? We already know that any future elements that we're going to swap in will have a lower multiplier value. So we don't really need to worry about the multiplier, because the multiplier will always be whatever we swap in, because that's guaranteed to be the lowest multiplier value. So what we were really looking for is if we swap in an element for one of these existing k elements, will it have a better value than the other element? So we need to calculate our first k elements. We need to find our base value. So we will have some result here. We will return our result at the end. All right, so then for every index in range k, so we'll find our first k values in our elements list here. So let's see, we'll need to keep track of a couple things. We'll need to keep track of the total value so far. And then we'll also need to keep track of the min multiplier so far. All right, first let's grab the element. So we'll grab the element at index I. Now this will be our value plus our multiplier. I'll just call it m. So that's the element at index I. Now our total will just increase by the value of that element. Now our minimum multiplier, that will just be whichever, actually that will be this new multiplier because we're guaranteed that these are in descending order. So we can just set our minimum m to this m. And at the end, our current result will equal our total times this multiplier, or this min multiplier. Okay, so that gives us our base value. Now we want to start swapping out elements. So if we keep looking down the line at k plus 1, so the indexed k plus 1 element, we can swap that in for another one of our elements already in this list. Which element do we swap it in for? Well, we definitely want to swap it in for an element that has the lowest value. So let's actually keep track of our elements so we know how we swap them in and out. So I'm going to call that a heap because this will be a minimum heap. Basically what we're doing here is we're going to keep track of our elements, keep track of which one has the minimum value. We can pop that one out and swap in our next element, which possibly has a higher value. Now we don't need to actually keep track of the entire element, we just need to keep track of its value here because the multiplier will always be whatever multiplier our current element is. Because we've sorted our elements by descending order of the multiplier, that means whatever the multiplier is for this element as we go through our list of sorted elements, that multiplier will guaranteed be the minimum multiplier. All right, so let's see, our heap will just append, well, I want to keep this as an actual heap. So we want to keep the minimum value at the top of the heap. So we will do a heap q append, or in this case, it's a heap push. And we put our heap and the value. So now we've got our elements, we're putting them on the heap, keeping track of the minimum value so far, and keeping track of our total value and this minimum multiplier. All right. So now we have our base result. The next step is to go through all of the remaining elements and figuring out if we swap in one of these remaining elements for the minimum valued current element in our heap, will that give us a better result? So that's pretty straightforward too. So for every index in a range, and let's see, we need to go from k to the length of our elements here. So we'll go through all the remaining elements. We'll pull out an element, so let's just grab the val and the m for each element. So the next thing to check here is just whether or not we have a better value than whatever the minimum value on our heap is. If we don't, then we'll just continue. We don't need to do anything. So if the value for this element is greater than the value, the min value of our heap, then we can swap out these elements and potentially get a higher result. So let's just do that. So we'll do a heap q. Actually, we need to keep track of this removed element. So our removed element will be, let's see, heap q, and we have to do a heap pop for the heap. Now we need to decrement our total by this value. So we're removing this element from our subsequence. We need to remove its value from our total. Now we need to increment our total, or increase our total, by the new value for this new element. We need to put this new element onto our heap and calculate our new result. So let's see, heap q dot heap push. And then our result will equal the maximum of either our current result or this new total times our new minimum multiplier, which will be m. Oh boy. Okay, so I think this is it. We've gone through, we've pulled out all of our elements so that we could sort them. Now each of these elements will just be the value of the element associated with the multiplier for the element. Then we sort them, and we're going to be sorting them by the multiplier in reverse order. Then we can go through, find our base score by finding the first k elements, summing their total, and multiplying it by their minimum multiplier. Once we've done that, we'll go through all the remaining elements. The key here is that we're keeping all of the elements in a heap. Now this is a minimum heap, meaning the smallest valued element will be at the top of the heap. Then we'll go through our remaining elements, and we can possibly replace the lowest element, the minimum element in our heap, with a new element, as long as that new element has a greater value than the lowest element in our heap. Because we already know it has a lower multiplier, and that new multiplier will become the minimum multiplier. So we want to make sure that we have an increase in value before we try to swap it out. If we do decide to swap it out, we will pop that minimum value from the heap. We will decrement our total by that removed amount, and then increase our total by this new element's value. Then we'll push our new element onto the heap. Then we will calculate our new result. It'll either be our current result or the total, this new total, times our new minimum value, our new minimum multiplier. Then we return the result. All right, I just need to add the heap to this, and let's try this. And we pass. All right, let's submit this and see how we do. And we do really well. All right, so we pass, we beat 91% for runtime and 23% for memory. So that is really good. All right, that's the power of heaps right there. So this one's tricky. I would actually say this is a medium plus problem. This is kind of on the difficult side of medium. A couple things we could do. We don't actually need to keep two separate for loops. We could make one for loop where we basically push and pop all the values depending on whether or not our heap is of length k. We can also do a zip here instead of doing our own for loop. Bunch of ways you can optimize this to get a little bit better score. But overall, I'd say a 91% is pretty darn good. All right, well that is it for me. Hope you enjoyed this, hope you had fun, hope you learned something, hope you can go out and write better code.